All right, folks, let's finish this off, and we'll call it a day. Just 2 more of these after today, guys. All right, so now we are going to consider the situation that we've been considering, but the slight difference is that the game is going to end at some point. It's not infinitely played, so everything that we've been talking about will come into play in the same way, but the difference is that there's an end to the game. Now, whether or not the players know when the game ends will also affect the outcome for the game, and whether or not the firms can maintain the collusive outcomes that we've been talking about. All right, so we'll consider 2 classes of finitely repeated games: games in which players do not know when the game will end, and games in which players know when it will end. So let's again consider them in turn. Games with an uncertain final period. Suppose 2 duopolists repeatedly play the pricing game, the Bertrand pricing game that we've been talking about, until their products become obsolete, at which point the game will end. So the products can become obsolete, or there might be a situation where the government comes in and says, oh, you can't sell this good anymore. So we'll look at that case in a second. We'll look at the advertising game for firms that sell cigarettes. So suppose the firms do not know the exact date at which their products will become obsolete. So the best way to analyze these situations is to incorporate a little bit of probability. So probability is something that is often used when using game theory. It, of course, complicates the analysis, but it also makes it more robust in terms of application. Like, we need to be putting into our analysis probabilities because, again, there is uncertainty. So we should be considering probabilities of different outcomes. So let's say the probability that the game will end can be represented by theta. That's just the Greek letter theta, a 0 with a line through it. Just a placeholder for, again, the probability that the game will end the next period. Theta is between 0 and 1. The probability of all events happening within a set of events is going to equal 1, the sum of all the probabilities. Either there will be individual probabilities for individual events that will sum to 1, or there's a probability that nothing happens, and therefore that is the outcome, and that has a probability of 1. Regardless of what the options are, the outcome is that something will happen, and therefore all probabilities sum to 1. So if you have a probability that the game will end tomorrow, and that's theta, then there's a probability the game will not end tomorrow, and that will be 1 minus theta. When a firm makes today's pricing decision, there's a chance that the game will be played again tomorrow, and there's a chance the game will not be played again tomorrow. If the game is played again tomorrow, there's a chance that it will be played again the next day, and so on. So let's say theta is 1/2. So there's a 50-50 chance the game will end after 1 play. That means there's a 1/2 times 1/2, which is a 1/4 probability that the game will end after a second play. More generally, there is a 1/2 raised to the tth power chance that the game will end after t plays of the game, with t again representing the times the game is played, the period. So if we're talking about the game being played 3 periods, then that would be 1/2 probability the game will be played tomorrow, 1/2 probability the game will be played the next day, 1/2 probability the game will be played the day after that. To get the probability of it lasting that long, you have to multiply 1/2 times 1/2 times 1/2, which is 1/2 raised to the 3rd power. When there is uncertainty regarding precisely when the game will end, this finitely repeated game will exactly mirror the analysis of infinitely repeated games. So again, when the players don't know when the game is going to end exactly, but they know that it will end, then they basically behave the same way as if the game was played indefinitely into the future. So the analysis that we just did in the last section applies here as well. You're going to get the same outcome. When the players don't know when the game will end, even though they know it will eventually end, they can maintain a collusive outcome. They can maintain this outcome via the trigger strategy. Again, the interest rate plays the same role. But in this case, probabilities will also play a role. So again, if the firms adopt trigger strategies and a firm deviates by charging a low price, the other firms will punish it by charging a low price until the game ends. For simplicity, assume that the interest rate is 0, so we don't have both a probability and interest rate at play. Let's just leave the interest rate at 0 for now, just to make the role that the probability plays easy to see. All right, so assume the interest rate is 0 so that the firms do not discount future profits. Given such trigger strategies, the question is whether or not firm A has an incentive to cheat by charging a low price. So if firm A cheats by charging a low price, then B will charge a high price. When B charges a high price, then A's profits obviously will be 50 today, but 0 in all subsequent periods of the game. If firm A cheats today, it will earn that $50 regardless of when the game ends. If firm A does not cheat, it will earn $10 today. In addition, there is a 1 minus theta probability the game will continue again tomorrow, in which case the firm will earn another $10. There is also a probability of 1 minus theta times 1 minus theta squared, that the game will not terminate after 2 plays, in which case A will earn yet another $10. So again, this is the probability the game will continue for 2 days. Carrying out this reasoning for all possible dates at which the game terminates, we see that if firm A cooperates, it can expect to earn $10 today plus 1 minus theta probability the game will be played tomorrow. If so, they'll earn $10 plus 1 minus theta squared, the game will be played the day after that, times the $10 they'll get then, etc., all the way to the future. This is also a sum of a geometric series, and it converges, in this case, to 10 over theta. Again, that's due to the mathematical properties of geometric series, which I won't explain here. Just take my word for it. This, if we were to continue this series indefinitely into the future, infinitely, then the sum would converge to this amount, 10 over theta. So the present value of the firm's cooperation profits into the future are 10 over theta, 10 over the probability of the game ending tomorrow. When theta equals 1, then firm A is certain that the game will end after 1 play, and therefore the present value of their cooperative profits is equal to $10. If theta is less than 1, the probability the game will end after 1 play is less than 1, so there's a chance they will play the game again, and the profits of cooperating are greater than $10. So let's say the probability the game will end is only 25%, then the present value of the profit stream is 10 over 0.25, which is equal to $40. So the important thing to notice is that when the game is repeated a finite but uncertain number of times, the benefits of cooperating look exactly like the benefits of cooperating in an infinitely repeated game, in which you have those $10 multiplied times 1 plus I over I. In a repeated game with an uncertain endpoint, and you have 1 minus theta probability that the game will continue, that 1 minus theta plays the role of the discount factor, 1 over 1 plus I. So it has the same sort of role of kind of discounting the future. Even though there's a probability the future will happen in terms of this game, that it will continue, there's also a probability it will not happen, and therefore the profits in the future are not viewed equally as profits today, because they may not come. And so the closer the profits are to the present, the more value they ultimately have, and those into the future wind up having a lower discounted value, not discounted by the interest rate, but discounted by the fact that there's a probability they won't even get realized. So players discount the future not because of the interest rate, but because they are not certain that the future plays will occur. In a finitely repeated game with an unknown endpoint, as we're talking about, that's the case we're talking about, firm A has no incentive to cheat if it expects to earn less from cheating than from not cheating. For the numbers in our example, firm A has no incentive to cheat if the profits from cheating, which equal $50, are less than or equal to the value of the cooperative profits all the way into the future, which are equal to 10 over the probability of the game ending tomorrow, 10 over theta. And again, we can solve for theta. So multiplying both sides by theta, dividing both sides by 50. So this is true if theta is less than or equal to 1/5. If the probability the game will end is 20% or less, then firm A has no incentive to cheat. And they value the profit stream into the future enough that it offsets the profits made today by cheating. If after each play of the game, the probability the game will end is less than 20%, firm A will lose more by cheating than it will gain. All right, since firm B's incentives are symmetric, the same is true for B. So B has the exact same situation. They face the exact same trade-off, essentially. So when oligopolistic firms compete a finite but uncertain number of times, it's possible for them to collude and charge high prices. So again, you can get that same type of outcome, even if they know that the game may end, but they don't know when it will end. The key is that there must be a sufficiently high probability the game will be played in subsequent periods. In the extreme case, where theta is equal to 1, where again, the probability the game will end tomorrow is 100%, then players are certain they will play the game only once. In this case, the profits of cheating, 50, are much greater than the profits of cooperating, which is 10, and collusion cannot work. When theta is equal to 1, the game is really, again, just a one-shot game, and the dominant strategy for each firm is to charge the low price. Quick demonstration problem. This is the example of the advertising game. Again, like I mentioned last time, 2 weeks ago. Firms that engage in certain product markets, advertising really doesn't have the effect of bringing in new customers, but more of like just cannibalizing customers from competitors. So in the cigarette industry, that's one case where, like, if the cigarette companies advertise, they're only going to take consumers away from their rivals. They're not necessarily going to bring in new smokers into the market. So they could both choose to advertise in order to offset the effects of each of the advertising of their rivals, and therefore they will spend money on advertising and they will make relatively zero profits. Or they could agree to not advertise. So both of them know that they're not going to bring in new consumers and they're only going to be trying to steal consumers from each other. And so if they don't advertise, they don't have to spend money on advertising, so the profits can be higher. So if they can have that kind of collusive agreement, then they'll wind up in a better situation. But of course, they could make that agreement and then one could choose to cheat on the agreement. And of course, there is an incentive for that. If this firm chooses to advertise while this firm maintains the agreement, this firm converts all of, Marlboro's customers to Camel customers, and firm B winds up getting all the profits, whereas firm A winds up losing. And the same happens for the other case. They're both symmetric. So firm A could be the one advertising while firm B chooses not to advertise, and firm A winds up getting all the profits because they steal all the customers, while firm B loses because they spend money. They just don't have any money coming in. Anyway, because both have an incentive to cheat, the Nash equilibrium for this game is for them to advertise. And that is the outcome of the one-shot game. So two cigarette manufacturers repeatedly play the following simultaneous move billboard advertising game with the featured payoff matrix. There is a 10% chance that the government will ban cigarette sales in any given year. So then the question is, can the firms collude by agreeing not to advertise given that condition? All right, so suppose the players have adopted a trigger strategy, as we know that they would do, because they've agreed not to advertise provided the other firm has not advertised in any previous period. If a firm deviates by advertising, the other firm will punish the offender by advertising until the game ends. If firm A cheats on the agreement, its profits are $20 today, but zero in all subsequent periods until the game terminates. If firm A does not cheat, it can expect to earn $10 today, plus 1 minus theta probability. The game will continue tomorrow. The government won't ban cigarettes, which is 90%, and they'll get that $10 tomorrow. Again, 1 minus theta squared, the probability that the game will continue for another 2 days, in which case then it will earn another $10 on that third day, etc., and so on and so forth. We know that this sum converges to 10 divided by the probability of the game ending tomorrow, the government banning cigarettes. 10 divided by 0.1, which is $100. So this assumes that the interest rate is 0. Again, we are keeping the analysis simple just to highlight the the role that the probability plays. Since $20 is what they would reap by cheating, is less than $100, firm A has no incentive to cheat. The incentives for firm B are symmetric, thus the firms can collude by using this type of trigger strategy. Questions? All right. All right. Now, if the firms do know when the game will end, then that completely changes the outcome, and essentially nobody is able to maintain a collusive outcome in that case, and that is because of what's called the end of period problem. So suppose the game is repeated some known finite number of times. So again, it's the pricing game. For simplicity, we suppose the game is repeated only twice. So the argument that follows applies even when the game is repeated a larger number of times, provided the players know precisely when the game will end and the game has only one Nash equilibrium. So as long as that's the case, then this analysis is going to be valid for cases beyond the one we're looking at. The important thing about repeating the game in 2 times is that in the second play of the game that there is no tomorrow, right? Tomorrow is the last round. After that, nothing. So there can be no consequences beyond the second round. So each firm has an incentive to use the same strategy during that period that it would use in the one-shot version of the game. So tomorrow has no tomorrow, and therefore tomorrow is a one-shot, and therefore the Nash equilibrium is for them to cheat on each other. So if firm A cheats the last round, B can't punish A for doing so. Firm B knows firm A has an incentive to charge a low price in period 2, the last period, and will likewise want to charge a low price in that period. Since both players know their opponents will charge a low price in the second period, the first period is essentially the last period. They know what people are going to do in the last period, and therefore in the second to last period today, they really know that there's no consequences to today's actions because tomorrow they know the outcome. Nobody is going to punish anybody tomorrow because everybody has an incentive to cheat tomorrow no matter what. So therefore today is the last period essentially. Since there is a tomorrow, but it is the last period, and each player knows what the opponent will do in the last period. Thus, in period 1, each player has an incentive to choose the same strategy as in a one-shot version of the game, since they cannot be punished in period 2 for their actions in period 1. Thus, the Nash equilibrium for the two-shot version of the game is to charge a low price each period as well. Each player earns 0 profits during each of the 2 periods. Collusion cannot work even if the game is played 1,000 periods, provided the firms know precisely when the game will end. At that point, any promises to cooperate made during previous periods will be broken because there is no way a player can be punished tomorrow for having broken the promise. Effectively, a player has an incentive to break a promise in the second to last period since there is no effective punishment during the last period. Because all the players know this, there's effectively no tomorrow in the third from the last period. This type of backward unraveling continues until the players realize no effective punishment can be used during any period. So as long as the players know when the game will end, they know that eventually cheating will happen, and therefore, again, if you do the backward unraveling, that gets us to today, in which there's no consequence tomorrow, because tomorrow there's no consequence for the next day, because eventually cheating will happen, and because that's inevitable, cheating just winds up happening today. The players charge low prices in every period right up to the known last period. So, again, when the players play a finitely repeated game, this type of pricing game, when they know that when the game will end, then there's no way to maintain a collusive outcome, and the Nash equilibrium will result. The low prices will be charged, 0 economic profits will be earned by the firms. Quick demonstration problem. You and a rival will play the game in the table 2 times. Suppose your strategy is to charge a high price each period, provided your opponent never charged a low price in any previous periods. Question is, how much will you earn? We're going to assume the interest rate is equal to 0. All right, so given your strategy, your opponent's best strategy is to charge a high price the first period and a low price the second period. To see why, note that if she charges a high price each period, she will earn $10 the first period and $10 the second period for a total of 20 units of profit. She does better by charging a high price the first period, getting that $50, I'm sorry, getting the $10 and a low price in the second period, earning the 50 units for a total of 60 units of profit. So you will earn 10 units the first period, but lose those 40 units the second period for a total loss of 30 units. Anyway, so it's the end of period problem. It's pretty self-explanatory at this point. Quick application of the end of period problem. When players know precisely when the repeated game will end, then we have what's known as the end of period problem. In the final period, there is no tomorrow, and there's no way to punish a player for doing something wrong in the last period. Consequently, in the last period, players will behave just as they would in a one-shot game. This section examines some implications of the end of period problem for managerial decisions. So just a quick application to resignations and quits. As long as the benefits of shirking, which is avoiding responsibility by workers, are less than the cost to workers of getting fired, workers will find it in their interest to work hard. When a worker announces that she or he plans to quit, though, and let's say they announce they're going to quit the next day, the cost of shirking to the worker winds up going down to zero. There's no threat to them of being fired at that point because they're going to quit the next day anyway. Since the worker does not plan to work tomorrow anyway, the benefits of shirking on the last day generally will exceed the expected cost. One possibility for the manager is to fire the worker as soon as she or he announces the plan to quit. So that's one way to avoid the end of period problem. That's not the best solution. In some instances, this should be avoided for legal restrictions, but there are better reasons to avoid this. If you adopt the strategy to fire somebody as soon as they tell you they're going to quit in order to avoid the end of period problem, then employees will start to expect it. The best strategy for a worker would be to wait and tell you at the end of the day that he or she plans to quit. So consequently, you will not solve the end of period problem, but instead you will be continuously surprised by worker resignations with no lead time to find new workers to replace them. A better managerial strategy is to provide some rewards for good work that extend beyond the termination of employment with your firm. Basically, you can emphasize to workers that you're pleased to write a letter of recommendation should a worker need one in the future, which then open-ends the interaction. There's no longer an end of period there. This sends a signal to the workers that quitting is not really the end of the game. Anyway, it's an application. It's not my favorite. You don't have to learn it. I'm going to get rid of these slides. I don't like them. I don't like the part of the course that tries to tell you, oh, this is how you can manipulate workers. It's just, people need to be treated like people, and that's it. Like, just have reasonable conversations with people, work out reasonable agreements with them. If they try to claim they took exams and didn't take them, that's a whole other issue. We won't talk about it. All right, anyway, multi-stage game. So this is the last part of the chapter. It deals with the sequential move games. We've been dealing with simultaneous move games in which the players make their moves at the same time. But if players make their moves sequentially, meaning like one player makes one move and then other players respond to that, then that changes the nature of the game. We can't use the normal form representation of the game. We use what's called the extensive form representation of the game. So an alternative class of games is called the multi-stage games. Multi-stage games differ from the class of games examined earlier in that timing is very important. In particular, the multi-stage framework permits players to make sequential rather than simultaneous decisions. All right, let's look at the theory on how this approach works. So to understand how multi-stage games differ from one-shot and infinitely repeated games, it's useful to introduce the extensive form of the game. An extensive form game summarizes who the players are, the information available to the players at each stage of the game, the strategies available to the players, the order of the moves of the game, and the payoffs that result from the alternative strategies. So we'll look at an example right now. Once again, the best way to understand the extensive form representation of the game is by way of an example. So here we have an extensive form of a game. The circles are called decision nodes, and each circle indicates that at the stage of the game, the particular player must choose a move. So this is the decision node for player A or player 1. and that denotes the beginning of the game, right? They make their move. They can either go up or down. Depending on what they do, then player B needs to also make a move, either choose up or down themselves, but in response to A. So therefore, there are two branches of possibilities for B. These are the decision nodes for B. And again, they're contingent upon what A does. The single point denoted A, at which all of the lines originate, is again the beginning of the game. The numbers at the ends of the branches are the payoffs at the end of the game. So within the parentheses, you have two numbers. The first number represents the payoffs to player A, or player 1, and the second number represents the payoff to player 2. In this game, player A moves first, then player B must respond with a move. So player A either goes up or down, and then B has to decide what to do in response to that. As in the simultaneous move games, each player's payoff depends not only on his or her actions, but on the actions of the other players as well. Even though player A gets to move first, their payoff will ultimately depend on what player B does. So if player A plays up, then depending on whether player B plays up or down, player A will either get 10 or 5. So there's an important difference between the sequential move game depicted in the figure and the simultaneous move games examined earlier via the normal form representation of the game, as opposed to the extensive form representation of the game. Since player A must make a decision before player B, A cannot make actions conditional on what B does. So A cannot say, A cannot say, well, if B responds by choosing up, then I can do this. No, they can't do anything. They have to make their move, and then B does what they do, and then that will lead to an outcome. So A can only choose to go up or down. In contrast, B does get to make their decision contingent on what A does. So a strategy for player B will specify an action for both of his decision nodes. If player A chooses up, then I will choose down. If player A chooses down, then I will choose up. In this case, if player A chooses up, player B can choose either up or down. If player A chooses down, player B can choose either up or down. One example of a strategy for B is to choose up if player A chooses up, and down if player A chooses down. So we would either wind up in this outcome or this outcome, in which case player B would wind up with 15 if player A played up, and player B would wind up with 20 if player A played down. So notice that player B's strategy is allowed to depend on what A has done, since this is a sequential move game and B moves second. In contrast, there's no conditional if in player A's strategy. To illustrate how strategies work in sequential move games, suppose player B's strategy is, I will choose down if player A chooses up, and down if player A chooses down. So in that case, B will choose down regardless of what A does. So that's a dominant strategy for B. Well, as far as what they would choose, it's not a dominant strategy in the classic sense, as we established earlier. I didn't mean to mention that, sorry. Forget that I said that. All right, anyway. So choose down if player A chooses up, and choose down if player A chooses down. So that means that if player A chooses up, B would get 5. If player A chooses down, B would get 20. Given the strategy, what is the best choice for player A? So in that case, we could look at the payoffs for player A, and obviously 6 is better than 5. So if B were to threaten to play down no matter what, then that would force player A to choose to play down, if they believe that that is what B would do. So if A chooses up, she earns 5, since B will choose down. If A chooses down, she earns 6, since B will choose down. Given a choice between earning 5 and 6, player A earns 6 and therefore will choose down. Given that player A chooses down, the question is, does player B have an incentive to change his strategy? So if player A chooses down, does B have an incentive to change the strategy of playing down? No, right? Because 20 is better than 0. So definitely they would choose to play down. B's strategy specifies that he chooses down if A chooses down. Believe me, I asked you that question for a very specific reason. We'll see in a second why. All right, by choosing down, B earns 20, whereas he earns 0 by choosing up. We thus see that B has no incentive to change his strategy given that A chooses down. Since neither player has an incentive to change his or her strategies, we found a Nash equilibrium for the game. So this is a Nash equilibrium for this game. Again, player A, if player A chooses up, player B chooses down. If player A chooses down, player B chooses down as well. And that will result in this outcome here. So again, player A down, player B down if player A chooses up, and down if player A chooses down. This is the Nash equilibrium for the game. This is how one would write it. The payoffs that result in this equilibrium are 6 for player A and 20 for player B. So you should ask yourself whether or not this is a reasonable outcome for the game. Like, is this an outcome that would actually happen in the game? In particular, notice that the highest payoff for player A results when player A chooses up and player B chooses up as well. That would result in player A getting 10. So the question is, why didn't player A choose up? So B threatened to play down no matter what. And so then player A believed that threat and chose to play down, because obviously if B is going to choose down no matter what, then 6 is better than 5. But the question is, should player A have believed this threat? If player A has chosen to play up, would player B actually have chosen down? Well, let's look at the payoffs. Clarissa, you said no? Would player B choose down if player A chooses up, given the payoffs? No, right? Player B would choose up because 15 is better than 5, right? So player A should not believe this threat, right? The threat is not credible. The threat was made so that B would get A to choose down so that B could then wind up with the highest payoff possible, which is 20, which is greater than 15. But that does not benefit A because then A winds up with 6 instead of 10, right? So if she chooses up, player B's best choice is up, since the payoff is 15, and that's better for B than the payoff of 5 that results from choosing down. But if B chooses up, A earns 10. This is higher than the payoff in that Nash equilibrium that we examined earlier. So what do we make of all this? There is, in fact, another Nash equilibrium for this game. In particular, suppose player B's strategy is choose up if player A chooses up, and choose down if player A chooses down. Obviously, those are the best choices for B. Given the strategy by player B, player A earns 10, choosing up, and 6 by choosing down. Clearly, the best response by A to this strategy by B is to play up. Given that player A chooses up, player B has no incentive to change his strategy once that's happened, and therefore we have another Nash equilibrium, which is this one here. In this Nash equilibrium, player A earns 10 and player B earns 15. So then the question is, which of the two Nash equilibrium outcomes is the more reasonable? This one, right? This is the more reasonable outcome. All right, so the reason is as follows. In the first Nash equilibrium, player A chooses down because player B threatened to choose down if player A chose up. But player A should recognize that this threat is not a credible threat. If this stage of the game, the decision node, were in fact reached, then player B would have an incentive to renege on the threat and choose down and not choose down. So if A actually were to choose up, given the fact that B threatened to choose down, once this happened, B would not choose down. So choosing down at this stage of the game would result in lower profits for B than he would earn by choosing up. Player B therefore has no incentive to do what he said he would do. In the jargon of game theory, the Nash equilibrium in which player A earns 6 and player B earns 20 is what's called not a sub-game perfect equilibrium. So this is not a sub-game perfect Nash equilibrium because it involves a non-credible threat. So a set of strategies constitute a sub-game perfect equilibrium if it is a Nash equilibrium. And 2, at each stage of the game, decision note, neither player can improve her payoff by changing her own strategy. So this is a sub-game perfect equilibrium. It involves all credible threats versus this one that involves the non-credible threat of B choosing against his own interests once A chooses up, choosing to get the lower payoff at that point. Yeah.
So just to clarify, A has this information, they just don't have the information of what B is doing.
Right.
And B has the same information.
Right. But B could
That's why they made the threat.
B could threaten to make this weird move that would then, if they were to do it, make A be in a worse position than if they just chose B, right, and just wound up here, which would get him 6, which is better than 5.
And by A going up, they can like trap them to just make either one of those rather than this first, second one, right?
Right. By A choosing up, well, I mean they would force the hand of the second player to choose the best option for them that would wind up benefiting A the most as well. And so that is a Nash equilibrium for the game, and it is a sub-game perfect Nash equilibrium for the game because it involves all credible threats versus the non-credible threat of I'll choose to screw myself because you chose something I don't like. All right, so a sub-game perfect equilibrium is a Nash equilibrium that involves only credible threats. The only sub-game perfect equilibrium involves player A choosing up and player B choosing up when player A chooses up. All right, now let's look at some applications of these multi-stage games. The first one is the entry game. Will a firm enter a market or not? So we looked at the contestable market situation at the end of the last chapter, where under a certain set of conditions, the firm that's operating the market is under threat of another firm coming in to compete against them, and therefore they are forced to choose to charge the lowest price possible, because if they don't, then a firm will enter the market, charge a lower price, undercut them, and basically price them out of the market. So this is a similar type of situation. To illustrate the use of the theory of a multi-stage game in a market setting, consider this extensive form of the game. Here B is an existing firm in the market, and firm A is a potential entrant. Firm A can either enter or not enter the market. If they enter the market, then the existing firm will have to compete against A. Firm A must decide whether to enter the market or stay out. If firm A decides to enter the market, then B must decide whether to engage in a price war, which is hard competition, versus soft war, which is to share the market. So the payoffs are measured in millions. There's 2 Nash equilibria in this game. The first occurs where the firm B threatens firm A to play hard if they were to enter, and thus A would stay out of the market. Is that a subgame perfect Nash equilibrium? Is it?
I don't even know why that one
It's after A has done the choice, if B is threatening to do something that is against their own interests, then that is not a subgame perfect. Then this is not, right? It's not, right? Because if B says, if you enter the market, I'm going to play hard, then that means that they're going to wind up in a price war. B's going to have to lower their prices and wind up like losing, essentially, profits that they could have earned. But in reality, B will not choose that. B will choose the soft sharing of the market because they will earn 5, which is greater than 1, right? And so it is not a sub-game perfect Nash equilibrium. So to see that these strategies indeed comprise a Nash equilibrium, note the following. Given that firm B's strategy is to choose hard if firm A enters, A's best choice is not to enter. Given that A doesn't enter, B may as well threaten to choose hard if A enters. So it's a threat. If A chooses to believe it, they'll stay out, and therefore this will be the Nash equilibrium for the game. Thus, neither firm has an incentive to change its strategy. Firm A earns 0 and firm B earns profits of 10 million. However, the Nash equilibrium involves a threat that is not credible. Again, we know that firm A chooses not to enter the reason firm A chooses not to enter is that firm B threatens to choose to play hard if firm A were to enter. So does B have an incentive to carry out the threat if choosing hard if firm A enters? Obviously not. The answer is no, since given that firm A enters the market, firm B will earn 5 million by playing soft and only 1 million by choosing to play hard. I already said all of this. This is one of those situations where I have not had time to edit down these slides, and I apologize for all the verbiage. I'll get to it eventually. Anyway, if firm A enters, it is not in firm B's best interest to play hard, obviously. They would play soft. Thus, the outcome in which firm A stays out of the market because firm B threatens to choose hard if it enters is a Nash equilibrium, but it is not a subgame perfect equilibrium, as we already established. It involves a threat that is not credible, namely the threat by firm B to engage in a price war if firm A enters. The other Nash equilibrium for this game is for firm A to choose in and for firm B to choose soft. So the other Nash equilibrium is this one here. In particular, if firm A enters, firm B's best choice is to play soft. By playing soft, they earn 5 million instead of 1 million. Given that firm B plays soft, if firm A enters, then A's best choice is to enter. By choosing in, A earns 5 million instead of 0 it would earn by staying out. So that is a sub-game perfect equilibrium. It involves a credible threat. If you enter, I will play soft. And that's it. So while there are two Nash equilibria for the entry game, there's a unique sub-game perfect equilibrium in which firm A chooses in and firm B plays soft. All right. I just want to emphasize to you guys like how powerful this method of like analyzing situations is, and how like it can provide like really useful insights. And the analysis gets more complicated than this because you have to throw in probabilities into it. And we won't do that in this class, but ultimately it winds up being a really useful tool to analyze like these sort of strategic interactions. All right, let's look at another application, innovation here. So our analysis of the entry game reveals an important lesson for future managers. It does not pay to heed threats made by rivals when the threats are not credible. We can also use the theory of sequential or multi-stage games to analyze innovation decisions, whether or not a firm should create a new product or not. And that will be illustrated by this demonstration problem. So your firm must decide whether or not to introduce a new product. If you introduce a new product, your rival will have to decide whether or not to clone the new product. The payoffs are given in millions. The negative loss represents a loss in R&D, which your rival doesn't need to spend in order to clone. So the question is, should you introduce a new product? The second question is, the second question requires that you set up the extensive form of this game, and the third asks how you would change your answer if your rival had promised not to clone your product. And then the last question is, what would you do if patent law prevented your rival from cloning your product? Here are the payoffs. If you don't introduce a new product, you and your rival will earn 1 million each. If you introduce a new product and your rival clones it, then you lose 5 million and your rival earns 20. If you introduce a new product and your rival doesn't clone, you earn 100 million and your rival earns 0. So make sure that this type of situation, if you're given information like this, you can set up an extensive form of the game. And if you're given information in a normal form situation, you can set up that as well. And you're able to distinguish between the two types. All right, so your firm must decide whether or not to introduce a new product. The payoffs are given in millions. The negative loss represents a loss in, again, research and development, which your rival doesn't need to spend in order to clone. So the first thing is to set up the extensive form of the game, which is set up here. So again, you can either introduce or not introduce the game. You don't introduce the game, you just maintain your level of profits, and so do they. You introduce it, they decide to clone it, you lose money in research and development, they earn profits because they cloned your product without having to invest any money to figure out how to make it. And the other option is for them not to clone your innovation. You get 100% of the profits and they just get 0. So the question is, should you introduce your new product? So again, just consider all the different options, right? Like, if you introduce your product, what is B likely to do? B is likely to clone it, right? Because 20 is better than 0. So therefore, your options are either introduce and get -5 or not introduce and get 1, right? So if you introduce a product, B's best choice is to clone, in which case you lose $5 million. If you introduce a product, you earn $1 million. Thus, your profit maximizing decision is not to introduce the new product. How would your answer change if your rival had promised not to clone the product? So the rival promises not to clone the product. If they promise not to clone the product, then we would wind up here, right? In which case you would earn 100, which is better than 1, right? So there's no credibility, but it is a Nash equilibrium, right? They do promise it. It's not a subgame perfect Nash equilibrium, though, right? So if you believe your rivals promise not to clone, you will earn 100 million by introducing a new product and only earn 1 million if you do not introduce it. However, B's promise is not credible, as we've already established. B would love you to spend money developing the product so that B could then clone it and earn profits of $20 million. In this case, you stand to lose this $5 million. Since the promise is not credible, you'd better think twice about letting it affect your behavior. What would you do if patent law prevented your rival from cloning the product? Introduce it, right? Because then you would wind up in this situation here where you definitely will get your profits. So if you can obtain a patent on your new product, B will be forced to abide by the law and refrain from cloning the product. In this case, you should introduce the product and you will earn the $100 million. This illustrates that the ability to patent a new product often induces firms to introduce products that they would not introduce in the absence of a patent system. Essentially just, again, highlighting the benefits of patents, which are good and bad things, because patents do give monopoly power to those that produce, which creates an efficiency of markets, which creates deadweight loss, which is a problem for society as a whole, but there is that trade-off of either that or no innovation. And if you guys remember your macro course, economic growth in the long run is due directly to technological advancements. So the subgame perfect equilibrium? So the subgame perfect Nash equilibrium is this one here without the patents. But if there is a patent, then this would be the subgame perfect Nash equilibrium. All right, let's look at, I think this might be the last one. All right, this is sequential bargaining. So we talked about a bargaining game in the last class. It was a one-shot simultaneous move game in which you had a union and a firm, and they were trying to figure out how to divide up a surplus of $100. And we figured out there were 3 Nash equilibria there. And so it was very uncertain what would happen in those situations, which reflected the nature of these kind of negotiations. They often result in stalemates because you will have various Nash equilibria, which means that it's difficult to get to an agreement. So the final application of the multi-stage game is another sequential move game, which is again a bargaining game. Specifically, suppose that a firm and a labor union are engaged in negotiations over how much of a $100 surplus will go to the union and how much will go to management. Suppose management moves first by offering an amount to the union. Given the offer, the union gets to decide to accept or reject the offer. If the offer is rejected, then neither party will receive anything. If the offer is accepted, the union gets the amount specified and management gets the residual. To simplify matters, we'll suppose the management can offer the union one of three amounts: $1, $50, or $99. So we can set up the extensive form of the game in this way here. So again, here's management. They can either offer $1, $50, or $99. And again, the union can either accept or reject at each of its decision nodes, depending on what the management does. So notice that the union gets to make its decision after it learns of management's offer, which is different than the case we considered at the end of the last class 2 weeks ago. Suppose you are management and the union makes the following statement to you before you make an offer. Give us $99 or else we will reject the offer. So the union is making a threat, essentially, that no matter what, if management doesn't offer the $99, they're going to reject the offer, which is credible or not credible? Not credible, right? Because if management were to offer either of these, then it would be in the union's best interest to accept it, because accepting it would be better in both cases. 1 is better than 0, 50 is better than 0. So the question is, what should you do? If you believe the union, then if you offered it a lower amount, it would reject the offer and you would get nothing. Given the union strategy, your best choice is to give the union $99 since the action gives you a payoff of $1 instead of 0. Remember, even though we want the agents, the people making decisions in these situations, to behave rationally, meaning that they're going to choose the outcomes that benefit them the most, sometimes that's not going to happen. People aren't going to behave rationally, right? They're not going to choose the outcome that benefits them the most. We saw that with the recent election. A lot of people chose this guy to lead them, and now he's eroding the government that is basically the safety net to a lot of these people that voted for him. And that's just the situation we live in. We live in a world where people will make seemingly non-credible threats, but then actually move forward with the irrational threats that they make. And it just won't make any sense ultimately. So even though we can identify Nash equilibria, subgame perfect Nash equilibria, and give a little bit more certainty about how a situation like this might unfold, in reality, anything could happen. But the analysis provides us a little bit of certainty as to how it might play out if the players behave rationally. So it's all contingent on rational behavior, which, is itself, might be a non-credible threat. All right, so again, given the union strategy, your best choice is to give the union the $99. Remember, the union is threatening to reject unless they get the $99. And given that you offer the union $99, its best choice is to obviously accept that offer and they get the $99. Because if they were to reject any of your other offers, then you would get 0 management, whereas in this situation, you at least get $1. Thus, one Nash equilibrium outcome for the game is this one here. So it yields $1 for management and $99 for the union. Is that a subgame perfect Nash equilibrium? No, right? It doesn't involve credible threats. So does this mean that the optimal action for management is to give the union $99? Obviously not. So notice that this equilibrium is supported by a union threat that's not credible. According to the union, if the management offered the union $1, the union would reject the offer. But by rejecting the offer, then they would put themselves in a worse position. Thus, it is not in the union's best interest to reject the offer. In fact, the unique subgame perfect equilibrium for this sequential bargaining game is for management to offer the union $1 and for the union to accept the offer. So management chooses the option that's going to benefit them the most. They're going to get the highest payoff out of all 3 options. And then beyond that, the union has to accept that offer because that's the best option for them, given that their alternative is to get 0. So that is the only subgame perfect Nash equilibrium in this game. All right. Let's do a demonstration problem, switching it up slightly with the union being the first mover and the management being the second mover, and that will be the end of the lecture. All right, so consider the bargaining game just described, but suppose the order of play is reversed in this case. The union gets to make an offer, and then management decides whether to accept the offer or reject it. What is the subgame perfect equilibrium outcome of this bargaining process? So again, to identify it, we got to figure out what is the outcome that's going to benefit the union the most. Offer $1, right? Offer $1 would then get the union the $99. And of course, by offering the $1, the management would have to accept it because rejecting it would be against their own self-interest. Again, you just consider these three options. The 99, the 50, and the 1. Obviously, 99 is the best. So again, the profit maximizing choice by management to any offer is to accept it if it yields more than $0. Management would earn by rejecting the offer. Therefore, the subgame perfect equilibrium is for the union to offer management $1 and keep 99 for itself. Given this offer, management's best choice is to accept it. Any threat by management to refuse an offer of $1 or $50 would not be credible. All right, this section has illustrated a remarkable feature of two-stage sequential bargaining games. Effectively, the first mover in the bargaining game makes a take-it-or-leave-it offer. The second mover can accept the offer or reject it and receive nothing. The player making the take-it-or-leave-it offer extracts virtually all the amount bargained over. The following example illustrates this principle. Suppose a customer wishes to buy a car that the dealer values at $10,000. The consumer values the car at $12,000. Effectively, the bargaining game is over the $2,000 difference between the consumer's valuation and the dealer's cost. Suppose the consumer makes the following take-it-or-leave-it offer to the dealer. I'll pay you $10,001 for the car. If you don't accept it, I'll buy a car from the dealer down the road. If the dealer believes the consumer's threat to terminate the bargaining process, if the offer is rejected, then he will accept the offer. The dealer prefers earning $1 to earning $0 by not selling the car. The consumer buys the car at $1 over the dealer's cost. In contrast, suppose the order of the bargaining process is reversed and the dealer tells the consumer another buyer wants the car, pay me $11,999 or I'll sell it to another customer. In that case, if the buyer believes the dealer's threat to sell to another buyer is credible and has no other options, her best choice is to buy the car since it costs $1 less than her valuation, the most that she's willing to pay. In this case, the dealer makes a handsome profit. So in concluding this section, we know that several aspects of reality often complicate sequential bargaining games. First, players do not always know the payoffs to other players. So if a car buyer does not know the dealer's cost for a car, he or she cannot make a take-it-or-leave-it offer and be assured of getting the car. Similarly, if a dealer does not know the maximum price a consumer will pay for a car, he or she cannot be assured of making a sale by making a take-it-or-leave-it offer. And that's why, ultimately, when we're actually using this approach in practice, we have to take probabilities into consideration because the payoffs aren't always transparent. Like, everybody doesn't always have perfect information. So that's where the probabilities come into play. But the insights that we gain from the approach are as legitimate. We're done. All right, folks. Good job surviving yet another lecture in this class. Thank you all for staying till the end. And we're done.